Hello, everyone, and welcome to Measuring Land Management Effects on Soil Dynamic Properties. Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Leo Rivera, whom I will introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and then we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, do not worry. We will be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with that out of the way, let's get started. Today, we'll hear from meter research scientist Leo Rivera, who will discuss how your land management decisions change your soil properties. Leo Rivera is a research scientist and director of science engagement at Meter Group. He earned his bachelor's and master's degrees in soil science at Texas A&M University, where he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Leo is the force behind application development in meters hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for field measurements of water content, water potential, and hydraulic properties of soil. So without further ado, I will hand it over to Leo to get us started.
All right. Well, thanks everyone for joining today's webinar. Today we're going to talk about, I think, a pretty fun topic. We're going to talk about dynamic soil properties and how we can use dynamic soil properties to better quantify impacts of management on soil. So before we really dive into that, kind of want to talk a little bit about why we even care about this, why this is important. So when we're thinking about our management practices, especially choices around things like tillage, whether we're talking about strip tillage, no-till, or conventional tillage practices, or if we're talking about grazing practices, whether we're talking about, continuous traditional grazing practices or some amplified paddock grazing, things like that. How do these choices impact our soil properties and how do they impact soil health? We're always trying to think about how we can actually quantify whether these changes are actually improving soil health. So what indicators, either in the field or in the lab, can we be looking at to understand how management changes impact both soil health, impact these properties, whether for the positive or the negative? And one of those tools that I think we can use to better understand and try and actually quantify how these practices are impacting soil health is looking at dynamic soil properties. Dynamic soil properties allow us to evaluate management along with the inherent soil properties, and we'll define the two, to link management practices to known soil health indicators. So let's talk a little more about dynamic soil properties. So the NRCS has a whole division or has a whole focus on dynamic soil properties. They have a dynamic soil properties group, and it's possible that that's name's changed a little bit, but they define dynamic soil properties, or they refer to them as those that are influenced by land use, management, and natural disturbances, and can be changing over time, while static soil properties or inherent soil properties are more characteristic of the soil's inherent nature and change less readily. So when we think about these dynamic soil properties, we can think of things like soil organic matter, we can infiltration rate and hydraulic conductivity, aggregate stability, bulk density, and water holding capacity. These are all really important properties that we want to understand. And these are properties that can be influenced by land use changes, by management, by things like that. Static soil properties are those properties that are characteristics of the soil's inherent nature. So things that we think about there are going to be things like soil texture. Typically, you don't see a big change in soil texture unless we're actually manipulating that. The type of clay that's present, the depth to bedrock, and the drainage class of the soil. Those are things that typically don't change. And you'll notice we have some of these highlighted in bold, or we have some of these bold in bold because these are measurements that we are familiar with making here at Meter Group. And we'll talk a little bit about some of those measurements now. So the tools for measuring dynamic soil properties have evolved a lot over the last 15 years. They've changed a lot just in my time here working at Meter Group, and especially from my time in grad school, but to now. The tools available have changed a lot and have really improved our ability to make these measurements. And so we had some of those things in bold. And so some of the things that we're able to measure, of course, are things like the soil moisture release curve in the lab using tools like the HYPROP and WP4C. We can measure hydraulic conductivity in the lab, which is also another good dynamic soil property to look at. Things that we can look at in the field are things like measuring soil moisture and water potential in the field, and actually looking at how those things might be changing over time, looking at how our water storage dynamics are changing. We can do some in situ retention curves to look at how those properties might be changing over time. Another field measurement that we can make is also just measuring hydraulic conductivity in the field with tools like the Satro to actually just make those measurements and do those evaluations in the field. And I'm not going to dive super deep into all of the principles of the measurements. We've done that in the past in several webinars, and we have a lot of resources available that dive into that. But I do want to hit today on, I think, what are some fundamentals behind these measurements that are important, especially for measuring dynamic soil properties. So one of those measurements that I'm really going to spend a lot of time on is hydraulic conductivity, because I think that's a really good indicator of how management is impacting some of these soil properties. Hydraulic conductivity, if you're not familiar with it, is a measure of the ability of porous medium to transmit water. What's beautiful about hydraulic conductivity is it's highly dependent on some very specific characteristics of soil, and we'll dive a little more into that, but it's really dependent on the size and the connection of the pore spaces of that soil, which can significantly be altered by management and land use changes. When we're talking about hydraulic conductivity, we're typically speaking either in terms of saturated hydraulic conductivity or unsaturated hydraulic conductivity. And here on the right, you see a graph showing how those curves change. You start at saturated on the right and then work towards unsaturated on the left for a few different soil types. We'll dive a little bit deeper into that, why that's important as we keep going. But to fully characterize the soil, both saturated and unsaturated hydraulic conductivity should be measured, because they really give us a full understanding of how some of these properties are changing. And I'll dive into why both are important right now. But before we do that, let's talk about things that impact hydraulic conductivity. And I think that'll help us better understand why this is a good indicator of how management is impacting these properties. So some of the factors that determine hydraulic conductivity are things like soil texture, which of course is one of those inherent soil properties, but that's just a part of the picture. Other things that really play a bigger role in what hydraulic conductivity can look like for soil is soil structure, biopores, so those are going to be things like worm channels, decayed root channels, things like that, compaction and bulk density. All three of those are factors that can be impacted by management choices and by land use and can change over time. Another thing that can also impact hydraulic conductivity is water content, the antecedent condition, so the antecedent soil moisture, the antecedent water potential, and those are things that can impact it, especially in expansive soils. That's a little trickier to kind of dive into, because there can be seasonal changes due to that, but we're not going to dive super deep into that today. So let's talk a little more about saturated hydraulic conductivity. So when we're talking about saturated hydraulic conductivity, it's specifically is the measurement of the movement of water when all pores are filled with water, right? It's saturated. So really simple look at what saturated hydraulic conductivity is. KSAT, or saturated hydraulic conductivity, is always going to be higher than the unsaturated hydraulic conductivity, because all of the pores are able to transmit water. And so you see that example on the right where, our KSAT is our highest value when we are at our zero water potential. So if you're looking at this chart, this graph shows conductivity on the y-axis and is showing water potential on the x-axis. And so as we get less negative, or get more negative, that means the soil is getting dry. That's our unsaturated hydraulic conductivity. One of the things you'll notice here is that here we have an example of a well-structured clay soil, a structureless sandy soil, and a poorly structured clay soil. And the thing that stands out is how much of an impact structure has, especially on the saturated hydraulic conductivity. And so this is something that's important to understand, and saturated hydraulic conductivity is significantly impacted by this, because macropores change, and those can significantly drive up how fast water can infiltrate into the soil. So it's a really powerful tool for looking at structure changes and improvements in our ability to actually infiltrate water into the soil. So now let's talk about unsaturated hydraulic conductivity. Unsaturated hydraulic conductivity is the measurement of movement of water at a given water potential or water content. So you'll notice that typically when we say KSI, or we're typically referencing a specific water potential because it changes as the soil gets drier. And so we need to understand that when we're trying to actually generate these curves. Unsaturated hydraulic conductivity is always going to be lower than saturated hydraulic conductivity because only a fraction of the pores are able to contribute to the transmission of water. Typically, unsaturated hydraulic conductivity is primarily governed by particle size distribution, so the texture of the soil, but it can be changed, especially if you see significant changes in bulk density. And so that's something that's important to understand. If we're seeing higher levels of compaction, that's going to change what your unsaturated hydraulic conductivity is going to look like. And so, these two things are telling you different things, and they're both important to understand. And so when I'm talking about, when we're thinking about hydraulic conductivity and how we can use it to assess things like soil health and how it's improving our soil, our dynamic soil properties and improving our soil's ability to infiltrate and store and retain water. There's a few things that we need to think about if we want to link this measurement to management changes, because hydraulic conductivity is, of course, dependent on many factors beyond management. It's, like we talked about, it is dependent on some of those inherent soil properties. And so what's helpful is if we can get some background data before the management changes have been put into place, or if we can actually get a site where we have similar soil types and compare those soil types across the different land uses, which you'll see that in a study that we're going to talk about here in just a little bit, how we were able to do that at a site that had been in the same management for over 70 years now, but had very similar soils across that whole site. So when we're trying to do that, so there's two approaches we can take this. We can either have similar soils in different land uses that we can do some comparisons that ideally that are hopefully in the same general area, or we can make measurements pre-management and then look at how management changes are impacting those measurements over time. So those are kind of two approaches, but I just want to really emphasize that if you're trying to use this measurement, it is super helpful to have that background data when trying to use this measurement to link it to how our management changes are improving our soil properties. Some other things that we want to think about, some other fundamentals for making these measurements to try and do some linkage between dynamic soil properties and management is, one, the differences between field and lab measurements. So when we're doing measurements in the field, typically we're looking at the entire interaction throughout that profile, which often is not present when we're taking samples back to the lab, because as you can imagine here, we have a soil profile, okay? When we're taking when we're taking samples to go do lab measurements, we're typically taking them from specific layers in the profile and then bringing them back to do measurements in the lab. And so really there, you're then segregating different layers of the soil and not really seeing what that entire interaction looks like. And there's other things that can also impact how lab measurements really compare with things that we see in the field. Ideally, field measurements typically give us a better understanding of sites in their undisturbed conditions, because we can do these measurements in the field, and typically the disturbance is pretty minimal to do these field measurements. And the scale is often different. So because of that, we often will need multiple lab measurements to really simulate and understand those interactions of the soils in the field. So let's talk about why you might choose one or the other. So when we're talking about field measurements, why we would choose field measurements? Well, one, field measurements allow us to actually, again, like I said, see the interactions through the profile, and get that characteristic of the soil, how it behaves together. I typically tend to think that field measurements give the best representation of the actual conditions. And oftentimes there's less disturbance than collecting soil samples for lab analysis. Now, there are ways, of course, to take your core samples and trying to minimize that impact in the field. and how much you disturb sites. But there are other factors at play, like how well did you collect that core sample? Are you taking intact core samples? How do the interconnectivity of those pores in that core sample match the interconnectivity of those pores of what we see in the field, things like that. But of course, there are limitations of field measurements as well. Some instruments, of course, do cause disturbance, especially if we're trying to install sensors for long-term monitoring. There's always some sort of disturbance that comes from that. Now, we have tools to try and minimize that disturbance using things like a borehole installation tool to minimize how much you disturb the site to get sensors in for long-term monitoring, things like that. And of course, some of these measurements are dependent on the field conditions, especially like KSAT, like we talked about. It can be dependent on some of the antecedent conditions, especially in expansive soils. And one other challenge is, of course, things like hydraulic conductivity is typically limited by the most limiting layer in the soil profile. So if we're making these measurements and the management changes that we're looking at don't really impact that limiting layer, you might not actually see any effects from management on these measurements. And this just varies site to site depending on what that profile looks like. But those are some of the limitations of these field measurements. So when we're talking about lab measurements, an advantage of lab measurements is that these instruments actually allow us to characterize individual segments of the soil profile. So that can be advantageous if that's what we're trying to do. If we're trying to specifically look, okay, how are properties changing just in the A horizon at the surface? Then we can take those samples and look at that and compare them versus some of the deeper layers as well. Lab measurements give us the best characterization of hydraulic conductivity, especially for those individual horizons. But when we're actually trying to get true saturated hydraulic conductivity, it's a lot easier to do that in the lab. The tools are better equipped for that. We can control things a lot better, especially because we can take those measurements in a controlled environment. Now, some of the limitations of lab measurements, of course, like I said, collecting samples can cause disturbance. And some of that disturbance might be either you're not taking an intact core, you may compact your sample a little bit, you may disturb the site. Another challenge that we see often when trying to compare lab and field measurements is that they don't always compare well. One thing that you could see happen is I take a core sample from the field and then it has, let's say was a decayed root channel or a wormhole in that core. Typically those end at some point in the profile, but if you have an open-ended pore in that core, your hydraulic conductivity is going to be a lot higher than what it might actually be in the field because of that. Another limitation of lab measurements is the sample size. Typically, these are smaller samples. And so because of that, we need to take more samples if we're trying to match, get a proper REV, which is a representative elementary volume, to try and characterize just the variability that we see in the field with these measurements, because we know that these measurements can be highly spatially variable. So we typically need to take more samples to try and match to try and properly characterize it, and especially when we're trying to compare that with some of the larger field measurements. And like I've already said before, these lab measurements don't typically quantify those interactions between soil layers because we're segregating those different layers. But if you take enough measurements, I think, and you take enough samples and you characterize it all together, I think you can overcome that with the lab measurements. So let's talk a little more about that. So now I'm going to dive into an example where we were actually trying to look at this. So we were trying to compare lab and field measurements, but also at the same time compare tillage effects on these measurements. So this was from a project we did about 3 years ago, where we were trying to look at conventional tillage versus no-till impacts on soil hydraulic properties on the Palouse. And so we did this research at Cook Agronomy Research Farm. The soils here are all Palouse silt loam. And what we wanted to do was compare two sites very close to each other that were both Palouse silt loam. One was in a conventional tillage operation, and the other was in a no-till operation. And so we wanted to compare, one, how did the land uses impact these soil hydraulic properties? And then how did the lab versus the field measurements compare across both sites? So how well did those compare? And so what we did is we actually took measurements in the field using the Saturo. So we took multiple measurements in the Satro in the field. And then we also took core samples from the same fields and measured them on the KSAT device in the lab to get the saturated hydraulic conductivity in the lab. And so here on the left, you can see a picture of those measurements being done in the field. And then on the right, you can see a chart showing the KSAT and then field saturated hydraulic conductivity comparisons across the land uses and across and between the lab versus the field measurements. And so the two charts, or the two bars on the left, the dark blue and the dark gray, show the measurements for our conventional tillage field. The dark blue is our lab, and the dark gray is our field measurements. And so when you compare the two, what's really cool about this is we do see difference in the spread. From our conventional tillage, we saw more spread in the lab measurements in terms of the variability of our hydraulic conductivity than what we saw with our field measurements of hydraulic conductivity. But if you look at the mean values of hydraulic conductivity across both, they were very close. They were pretty much right on top of each other, showing that we had enough measurements of both to get properly characterize the mean hydraulic conductivity for the sites. And so because of that, we were able to get really good comparison for that between our lab and our field measurements. In the no-till site, we saw a slightly different behavior. So we saw in the field, so the light gray for the no-till site is our field measurements, and the light blue is the hydraulic conductivity values based on the lab measurements. And again, we see a difference in the spread. We actually see more spread in the no-till site across the field, likely due to we expect to see more variability in some of those macropores because the structure staying intact, things like that. But so that's just part of it. But again, what we see here is our mean values across both the field and lab measurements are very close to each other. So I think the take home here is that if you have enough measurements to properly characterize the mean, you could choose to do lab or field measurements. But I think one of the critical things is just getting enough measurements to actually characterize those values. And one thing I didn't hit on earlier is there is a difference in the time that it takes, but with the lab versus the field measurements. Lab measurements, we can take core samples, bring them back, store them, do the measurements as we need to. Whereas with field measurements, we're out in the field making our measurements for several hours. We're very limited to being able to do those measurements within that time frame. And that can be a challenge. So time is another piece that you need to think about when you're trying to think about lab versus field measurements and which is going to work best for you. Okay, so we've talked about some of these measurements, and now let's dive into looking at some of these measurements in practice to actually look at dynamic soil properties and how they're changing across land uses. So first, I want to talk about some earlier work. This was actually work that I did in grad school looking at land use and landscape impacts on soil properties, soil hydraulic properties, and soil physical properties. And you'll see I put this in quote, early soil health work. This was, of course, done before soil health was was a common topic. In this study, we were just really trying to characterize how is land use affecting these properties, these soil properties. And so with this study, we wanted to compare 3 different land uses. We wanted to compare improved pasture site. You can see a picture of that site on the upper right, which is just traditional, conventional, or continuous grazing site. We wanted to compare it against conventional tillage site, which was in a corn, wheat rotation, which you can see that image that field in the image in the middle. And then a tall grass native prairie, which you can see in the bottom right. And you can also see the old double ring infiltrometer setup that we used for these measurements during that study. This was probably about 17 years ago now. So this research site was located in the USDA ARS Riesel watershed in the Blackland Prairie. This is a really cool area to do work in. This area has been in the same land use management. All of these fields have been in the same land use since the 1940s when this research station was created. The soils on this site are all predominantly mapped as Houston Black and Hayden Clay. And so we had very similar soil types across the site. The primary difference between Hayden Clay and Houston Black is the depth of parent material. So outside of that, at the very surface, the soil properties are very similar between the two. So what we did as a part of this work is one of the first things we actually did is we mapped these sites. So here you can see an example of one of the maps that we did to try and characterize some of the variability across the sites. And then we used that to help select where to make our measurements. But what we were doing was both looking at variability across the field, just trying to delineate some of those zones of variability, and also trying to look at landscape position effects as well. And so you'll see we were looking at primarily the summit, the back slope, and the foot slope when we're trying to look at what we call the Katina effect, and how this hill slope, these hill slope positions impact some of these soil properties. And of course, looking across the different land uses. So we mapped our sites, and then we went out and did a lot of measurements. We measured hydraulic conductivity, we measured soil organic carbon, bulk density. We did full soil mapping out there, and looked at organic. Yeah, so there are several things that we looked at as a part of this. And so we're going to dive into what some of that looked like. So in this chart on the right here, you can see how the hydraulic conductivity measurements compared across these sites, both by land use and by landscape position. And so what we see when looking at some of these effects, one, if you look at the two sites that aren't getting tilled, which is the improved pasture and the native prairie, we see a pretty similar effect of how the landscape position is affecting the soil hydraulic properties. You see lower hydraulic conductivities in the foot slope positions, the highest hydraulic conductivities typically in the back slope position, and in the intermediate is our summit, which is at the very top of the hill slope. And so we were able to characterize what that Katina effect kind of looked like on these soil hydraulic properties. But of course, what we also saw was that we saw higher hydraulic conductivities in the native prairie than what we saw in the improved pasture. And then as we moved over to the conventional tillage site, we see that we kind of lose some of that effect of the Katina on the soil hydraulic properties. We actually saw higher hydraulic conductivities in the foot slope than we did in the back slope or summit. We also saw higher hydraulic conductivities in the conventional tillage field. Now, some of that has to do because of the timing of when we made those measurements. We made those measurements post tillage and pre-planting. And so because of that, the soil there was still pretty recently disturbed. It hadn't had a lot of time to consolidate and settle. When we went back, and if we were to go back and make those measurements again later in the season, after the time it had to settle, we would have seen a bigger reduction in hydraulic conductivity in the conventional tillage site because all that structure had been destroyed. Looking at some of the other measurements on this site, so we also looked at things like soil organic carbon and bulk density. Also saw how the soil water retention curve was impacted by these different land uses. And what's really cool is if you just look at those three measurements, and these are all things that we refer to as being kind of these dynamic soil properties, you can see that we see a big difference in organic carbon across the three sites. We see the highest organic carbon, of course, being in our native prairie site, and our intermediate being in the improved pasture, and the lowest organic carbon in the conventional tillage site. And then what we see is we saw some differences in bulk density across all three sites as well, which makes sense. We see difference in bulk density across the land uses. And then we also saw an impact on the actual soil water retention curve of these three sites as well. So we saw a big difference, especially from the conventional tillage site to the improved pasture and native prairie in the retention properties and what that looked like. Okay, so that was an older study, of course, but since then, many studies have been done looking at these dynamic soil properties, well beyond what we're going to talk about today. But I want to just highlight one of them today, and kind of talk about this study from Applebaum et al. But let's give a little background here before we dive super deep into it. So, grazing ecosystems have co-evolved with ruminant grasses and soil biota contributing to carbon-rich soils over the last 40 million years. This is something that we're well aware of. This coevolution contributed to the global expansion of carbon-rich soils, especially in grassland regions, which cover approximately 40% of the global land area. However, modern practices have often degraded these ecosystems. In most rangelands, free-ranging wild herbivores have been replaced by fenced-in livestock. We see this in many areas where we've converted these prairies to grazing lands for cattle production, things like that. This shift has often led to the degradation of the vegetation and soils, resulting in declines in productivity, biodiversity, and in ecosystem resilience. Because of this challenge, various grazing management strategies have been developed to provide sustainable resource, to provide a more sustainable resource from the soil, and hopefully to provide better economic outcomes as well. And these include looking at things like continuous grazing, rotational grazing, and what's referred to as adaptive multi-paddock grazing, or AMP. And so the goal of the study from Affelbaum et al. Was to actually compare the continuous grazing and the AMP grazing, or the amplified multi-paddock grazing, in the southeastern U.S. If you're not familiar with what AMP grazing is, it involves grazing events that are short with planned recovery periods. So they're constantly moving sections around, allowing the soil sites to recover, while continuous grazing, as the name states, is continuous grazing with no planned recovery. So the study examines the effects of both the AMP and the continuous grazing management on plant species richness, on diversity and dominance and cover. They also looked at vegetation standing, crop biomass. They looked at water infiltration and hydraulic conductivity. And then they also looked at soil carbon levels, amount of bare ground, the fine litter cover, and the nutrient cycling across these sites. So we talked a little bit about how do you do some of these comparisons to try and make sure you're not just taking into account you're separating out some of those inherent soil properties. So what they did is this study method utilized what they called the across the fence comparison framework. So the study used paired ranches with similar biophysical conditions, things like soil type, climate, things like that, and comparing the AMP and continuous grazing within those areas. Their measurements included plant species richness, biomass, water infiltration, and soil carbon, and data were collected from ranches in Kentucky, Tennessee, Alabama, and Mississippi. So the results of their findings showed differences in a few areas, and you can see some of that here. When looking at vegetation cover impacts, the AMP, or the amplified multi-paddock grazing, increased vegetation cover. It increased diversity, especially in the southern sites. The continuous grazing sites typically had more bare ground and less plant cover, which makes sense with just, continuous impact on those sites. But they also saw grazing impacts on soil hydraulic properties and water infiltration. They found that the AMP sites generally had higher water infiltration rates and higher saturated hydraulic conductivities, which we think of this as being an indicator of better soil health. The soil has better structure. It's more able to infiltrate and store water for long-term sustainability of that site, to be able to support the grass that they're trying to grow. Lastly, the AMP sites typically had higher soil organic carbon stocks, which therefore enhanced the soil fertility and also increased carbon sequestration. So what Affelbaum et al. Concluded was that overall AMP grazing mimics natural grazing patterns. And so this improved the soil health, improved the vegetation diversity, and it supported higher livestock densities, and because of this, it both provides ecological and economic benefits for the ranchers. And the study suggests that AMP grazing can be a sustainable practice for ranchers to improve soil health and also improve ranch productivity as well in the southeastern U.S. So the last study that we're going to talk about is a newer one. This is from the Colorado STAR program. If you're not familiar with STAR, it stands for Saving Tomorrow's Agricultural Resources. The STAR program isn't just in Colorado. It's broader than that, but we're going to focus on the Colorado STAR program. The Colorado Soil Health Program is working with farmers and ranchers to balance vital changes without risking their livelihoods. So they're trying to work with growers to help them understand how some of their management impacts can improve the long-term viability and sustainability of the soils in their area, which is a resource, and has to be treated like a resource. And so some of the things that they were working with these growers, this is a study that's covering a broad section of the state of Colorado. This is a pretty large study. They're looking at things like cover crops, crop rotations, and grazing techniques. Are working with the different individual departments of ag in the area that are working directly with the growers. And again, so we talked about, okay, with that previous study, they utilized that across the fence framework where they were able to compare the soils or compare areas, sites with similar soils and climate conditions to try and evaluate the impacts of management. With this program, with this study, they're actually taking the other approach that we talked about, where you try and get some baseline data. So you start monitoring, and what they're doing is they're going to monitor things like soil moisture and look at how soil moisture storage changes over time. They're going to conduct soil testing over a 3-year period, getting that baseline data initially, and then getting data as over each year to see how these things are changing over time. And then they're going to report these results back to the grower. And so what's nice about this project is they're working with the growers. It's pretty minimal impact on the growers. They're really just providing tools to monitor and the data so they can see how their management choices are actually impacting these soil properties, and trying to make it possible for them to actually make these changes without really impacting their ability to be productive growers and do the things that they need to do. And so this is a really cool project. This is going to be an ongoing project where they're looking at these changes over time and trying to work with the growers to show how their management is impacting these soil properties and how, the positives and the negatives of what they're doing. So it'll be a really cool one to see how that continues to go. And I know there are other projects looking at similar things. And so it's going to be fun to see how this work continues to go, to grow, and how we can use these measurements to better understand how our management choices are impacting soil properties, both for the positive and the negative. And with that is all I have.
Awesome. Thank you, Leo. All right. We are going to take the next few minutes. Maybe we can get to 10 minutes for some questions from the audience here. Thank you to everybody who sent in questions already. There's still plenty of time to submit your questions if you'd like, and we'll try to get to as many as we can before we finish. If we do not get to your question, we do have them recorded, and Leo or somebody else from our meter team of specialists and scientists will be able to get back to you with an answer via the email that you registered with. All right. Let's see. We've got first question. I'm just going to read this because it's a great question here. So they are asking, this is a quote. This is not me, but so they say, I really appreciate how you're integrating soil physical properties into soil health analyses. It's an aspect that's often overlooked. During my master's, funny enough, at Texas A&M as well, I worked with the HYPROP system and saw its strong potential in soil health research. So, question here. From an agricultural perspective, though, I'm curious, how can this test be framed in a way that would make farmers consider having it done? So I guess we could talk about either using the HYPROP or just looking at soil dynamic properties in general.
Yeah, that's a great question, and great to have a question from another Aggie. That's actually a challenging one, because it is, doing tests like that is hard to convince a grower of why they would want to do something like that. I think a good example of this is probably what they're doing as a part of like the STAR program is where they're really treating it as a resource to the growers and trying to provide the service, and taking those measurements and getting those baseline data, and then making measurements over time, and how that's actually impacting, how their management is impacting what those properties look like. I think it's something that we would have to do, where we're providing the data and doing the data collection and working with the growers to do this, because this is not something that they're going to go out and do out their own in most cases. But having said that, I think there can be useful information just in generating those retention curve data for growers, because the growers are oftentimes looking at things in terms of soil moisture. And if we can use the retention curve data as well to help them better understand, hey, here's some critical soil moisture levels for you based on this retention curve, so they better understand, hey, here's my permanent wilting point, here's, especially depending on specific crops, here's kind of my stress points. Now I better understand what my soil moisture levels mean in terms of my crop response. And so trying to use it that way as well. But yeah, it's tricky. I think trying to get this type of data more accessible and more usable for growers is going to be a challenge.
All right. Here's another good one for you, Leo. All right. Getting a bit potentially technical here. So their question. So K is a tensor, and most of our models require each of a Kx, Ky, Kz, something along those lines. In the lab, we get Kx or Kz depending on core orientation. In the field, we get an effective K, so the mean of Kx, Ky, Kz. How do you reconcile the differences of measurement scale and composition?
That is a fully loaded question. I think it's a good one, though. I think this goes back to, again, of just talking about how we utilize the lab versus the field measurements for some of this. And of course, this depends on what you're doing. When we're modeling, we need those individual, we need typically that the lab measurements of K to put into our models so we can actually segregate that by layer, do those interactions. But one thing that we found, you saw that from the one study that we showed, is that if you get enough measurements, the mean K values, whether it's the lab or the field, compare well. And so I think it just comes down to getting enough measurements to actually characterize that. But again, it also goes back to how you're using these data. If I'm modeling, oftentimes the lab values are more useful for modeling practices, but actually trying to just understand infiltration dynamics in the field, I tend to lean towards the field measurements. But again, if you get enough measurements, you're going to properly characterize the mean anyways. And if you're trying to characterize different layers, whether in the field or in the lab, there are ways to segregate those different layers in the field too. We can use the borehole measurement methods to actually measure down at deeper layers to understand what those different layers are doing.
All right. This next individual is asking, is there any effect of, let me rephrase this. Does soil compaction have any effect on soil texture?
Yeah, no, typically not. So soil compaction should not impact soil texture. It's just going to impact, the overall density. It's going to impact a lot of other properties for sure. The only thing that's really going to impact soil texture, because again, that's one of those static or inherent soil properties, is if we're doing things like deep ripping, for example, that's actually intermixing some of those layers. That's the type of stuff that can actually cause some of that. Another thing that can kind of impact some of that is in expansive soils, we do see actual churning of the soil as those cracks open up, soil falls in, and you get movement of some of the soil up as it expands. But this is something that happens over a very long time period.
All right. This next individual is asking about sample strategy here. So how can they choose where to sample so that management differences actually show up? You showed doing transects. So do you do transects? Do you do a grid setup? Do you separate by slope or soil type? And then usually, how many samples do you need to get a representative coverage, or to be able to see, to reliably see the real effects in your data?
Yeah, that's a really good question. And one of my favorite things, actually, because that is a super big challenge, because we know that even just looking across a field, whether or not we're looking at land management impacts, is there's a lot of variability across the field as is. So what I recommend, and what we did as a part of our study, is we tried to characterize that variability, both by looking at the soil maps for that site, but then going out and doing the bulk EC mapping, because the bulk EC is responding to a variety of things, responding to things like depth of parent material, changes in soil texture, changes in conductivity, things like that. That helped us delineate some of those zones of variability. Then from there, we said, okay, these are our variability zones, but we're also looking at hill slope positions. So we need to make sure we have enough measurements in the different hill slope positions across also the different zones that we characterize the variability using the mapping. And so we kind of set up our sampling scheme that way, and then chose randomized spots to make sure that we're covering both the landscape positions, the zones of variability, and of course then looking at the different land uses as well. Now what that means though is it's a lot of measurements. So for that study, we did over 300 measurements across the fields. So it was a lot of measurements, which isn't feasible for everyone. And so you kind of have to choose, okay, how many measurements can I feasibly do, and then try to maximize your ability to cover the variability that we're going to see across the field. And so it can be challenging, but utilize the tools that are out there to help us figure out where those zones are.
All right. I think we are getting close to the end of the time. I think this is going to be our last question. Actually, it's a group of questions. I'm going to kind of paraphrase and group a couple of different questions in here. There, along with the sampling strategy, there's others that are asking about just kind of the general, project setup and experimentation process. And one of the main themes from some of these questions is, just in general, when you're trying to look at dynamic soil properties, what kind of sensors should they be using? We've mentioned a couple in this presentation and in the question session here. What kind of frequency should you be taking those measurements at? How do you deal with stuff that happens? Whether it's hysteresis or soil crusting or other stuff that happens during the field season or the measurement season. Can you go into a little bit more detail about just kind of that process of what you need to do to really set up and monitor your project?
Yeah, I am by no means the expert on the framework to use for looking at soil health. I think there's a lot of resources out there from places like Soil Health Institute, from there's the Cornell Shape framework. There's different frameworks that you can use to try and do this evaluation. And some are more simplified, others are much more complex and mean a lot more measurements. I think, it's really just trying to look at the tools you have available to make these measurements and trying to use the framework that works best for trying to go out and characterize these soil health and these dynamic soil properties. NRCS also has that dynamic soil properties group that's going out and making these measurements as well. And they're using tools like the Saturo, and they're doing other measurements as well along with that to try and characterize these dynamic soil properties. And so, I would either say, establish what your framework is going to look like. Because this is it's a fully loaded question, so there's a lot of approaches you could take to this, but you figure out the tools you have available and establish a framework that's going to work for your study. And in some cases, it could be more long-term monitoring, just going out and deploying sensors and looking at changes over time, like what they're doing with the STAR program. Or it can be actually going out and doing in-field measurements, like measuring hydraulic conductivity, measuring aggregate stability, measuring changes in bulk density, organic carbon retention properties, things like that, which can be really powerful. But it also, again, like I said, I think it's also important that you really have those baseline data, whether it's by comparing land uses or comparing sites with similar soil types and climate conditions across the different land uses, or if you're just trying to look at that change over time, that's going to change, I think that is also going to change how you decide to evaluate these properties. But I think just utilizing, figuring out what tools you have available and your time frame, especially too, to try and make these measurements, and then looking at the different frameworks that are out there and trying to think, okay, maybe the SHAPE framework works best for me, or maybe what Soil Health Institute is doing works best for me, and just looking at those. But yeah, it can be tricky. There's a lot of ways to go out, and we see a lot of people going out and coming up with their own ways of trying to evaluate soil health. And so yeah, there's many ways that you can go.
All right. Okay. That is going to wrap it up for us today. Thank you again for all the great questions. We hope you enjoyed this discussion. If we did not get to your questions, and there are several that we did not get to, we do have them recorded, and Leo or another one of our experts here at our meter team will be able to get back to you via email to answer your question directly. Also, please consider answering the short survey that'll appear after the webinar is finished, just to let us know what types of webinars you'd like to see in the future. And for more information on what you've seen today, check us out on YouTube and visit us at metergroup.com. Finally, look for the recording of today's presentation in your email, and stay tuned for future meter webinars. Thanks again, stay safe, and have a great day.